So about Silicon Austria Labs, we are a public-private partnership research institute. We are located at 3 sites in Austria, in Linz, Graz, and Villach, mostly publicly owned. And well, we do conduct applied industry oriented research. So we cover a fairly broad spectrum of topics and research areas. For instance, MEMS, piezos, wireless systems, also power electronics a lot recently. We are involved in the pilot lines for the ion traps from the European Union funding, embedded systems as well, and last but not least, sensor systems. So in the sensor systems division, I work at the Photonics systems group. And here you can see a more or less random selection of recent and also partly ongoing projects in our group. So in our group we are like 2070 now, I think, researchers. And you can see we also do fairly kind of different topics, really. Sometimes integrated photonics, especially for sensing. But also gas sensing of larger systems here for fuel cell tests. We are also doing combined MEMS and optical systems. So for instance, here you see a miniaturized MEMS FTIR system that we developed. LIDAR is also a big topic for the automotive. We are involved in testing setups, but also time-of-flight systems that we develop our own. For the semiconductor industry, chip holography for failure analysis, so bending of chips under certain environmental conditions, monitored in this case holographically. And also highlight always is the specialty laser developed, basically very robust, high power laser where the active medium rod is actually the cavity. And this is used for Ariane 5 laser rocket ignition. Recently also in quantum sensing, there are new activities. And later I will talk about our recent efforts to basically technology transfer in the area of nonlinear spectroscopy, what can be utilized for industry use cases. These kind of projects, they are mostly so-called cooperative projects. So we do contract research also, in the sense contract research means the company, like an industry partner, approaches us and basically pays us for research. They get everything, all the IP and so on, but have to pay the full cost. But SAL is publicly funded, so we sit on our own secured public funding, but we can only use that when it's triggered by industry interest. And this works like this, that basically 50% of the total project volume in such a cooperative model basically is covered by the project partner, by the industry, half of which is industry in kind. So the industry's own man hours, machine hours, or let's say a sample preparation or something like that, that can be built to the project. And 25% of the total project volume is then only cash from the industry. So this makes us very competitive, but is still under the European state aid law. Which we have to obey to this, of course. And 50% then of the total cost comes from our public funding, but it has to be triggered by joint interest from the industry, basically. We also do like these ordinary funding calls, most recent stuff from the European Union, many Horizon projects. But we currently have a very interesting national funding call. So we are in Austria, so this is the FFG for industry-oriented research public funding. So this is basically fully funded with a certain funding rate, basically. And the topic is laser technology for production environment, laser-based quality control. And what I will speak about in a second fits very well to this. So second harmonic generation for semiconductor interface metrology. And yeah, if you find the next 2 slides interesting, then feel free to approach me. We are looking for interested parties to build a consortium for this funding call. So if you're involved in any semiconductor equipment provider in any sense or manufacturer or similar, this would be a great fit. So from the physics or from the measurement principle, what is this about? So the thing is called electric field induced second harmonics. And this is essentially exactly what it says. So the shortcut is EFISH. And what you do is you measure basically the electric field with a laser, like remote, spatially resolved, non-contact. And for this, you utilize nonlinear optics. And the use case in the semiconductor industry is interfaces, because interface quality is highly critical to many devices, also in the process development, but also on the final device. So for instance, historically speaking, the silicon oxide interface, the big breakthrough before silicon semiconductors took off basically was to have the passivation of the silicon, which led to a super good surface quality. So without a good interface, basically we would not have silicon integrated circuits today. But still, with new materials, it's always a topic to have good interface quality on nanoscales, but also for large areas, let's say for silicon carbide MOSFETs, because, well, you get tunneling, you get leakage currents, and you have to control this to get good device performance. So interfaces and interface quality is always extremely critical. And when you have defects at an interface, you can trap charges there. And this is exactly then where the eFish plays into. So you have trapped charges at interface defects, and then you build up an electric field. And the electric field is especially strong due to the thin oxide layers that you typically have in the semiconductor industry. And therefore gets a lot of volts per distance. Yeah? And it doesn't really matter how you generate the charges, but you can either utilize the infrared laser that is then later also used as the interrogation beam, or you can use UV light, rather weak UV light, to populate the electronic traps basically, or you can use an active device and measure in situ on an active device. When you have this electric field, the static electric field, it basically, as this equation shows, it acts as a second order nonlinearity in disguise and generating the frequency doubled light, which you then detect, and then it tells you this frequency, the amount of frequency doubled light basically tells you how much electric field was there, and this can tell you something about the defect situation at the interface. So the implementation depends, of course, in details on the use case, but this is like a prototypical implementation drawn here. You have one ingoing beam for the infrared laser, one detection pass. You can use imaging configuration with a camera, or you can use just a bucket detector. Will make a point-like measurement. And optionally, you want maybe a dedicated channel for the pumping of the traps. So for instance, some weak UV light source. And here you can see an example measurement. The first block here in the measurement, you see the red curve, nothing happens basically, just some basic offset. The infrared light was weak here, so there's no multiphoton ionization. And then we turn on the UV light, the traps in the interface layer get quickly populated. And then you can measure after you populated the traps, you can measure on the plateau, and the measurement on the plateau is fairly quick. So you get a data point in a millisecond or something. So this is, in terms of throughput, it's sensible to speak about in situ implementation for this. So you can measure rather fast with this once you have populated the traps. So when you do transient measurements and not want to make just a quick interrogation after the traps are populated, when you make transient measurements like these here below, there are 3 examples here for different wavelengths, then you get such multi-exponential curves. And there you see the dynamics, the balance of the pumping of the traps and the decay of the traps. And this is very similar in terms of interpretation to what is known as deep-level transient spectroscopy, or the slow version, which is called Laplace deep-level transient spectroscopy, where you look at these multi-exponential decays or rises. But this DLTS is a contact measurement, so it doesn't have spatial resolution like an optical interrogation. And you need a contact, and you even need an active device for this. And for eFish, you do not need all this. You can use it on passive devices. It just needs some interfaces, basically. You can also use it on active devices, but not necessarily only on them. And you also have a new degree of freedom, the wavelengths that you can choose to optimize to various requirements. And you can, for instance, as you can see here, if you resonantly hit the trap level, basically, you can ionize it resonantly, which you then can use to optically remove the charges again. The exact physics of this, it's still disputed, but I think it could be utilized easily for metrology applications. Yeah, you get a lot of interesting features. Of course, it has been shown that you can detect metal contamination on wafers, which I think is a current big topic for certain metrology companies. Well, as I already said, active devices, you can sacrifice resolution for working distance if you want to measure an environment where you cannot go that close to the wafer for other reasons, because maybe it's in a process and you need access for other things. What is a bit difficult, but it's not a total showstopper, is non-centrosymmetric substrates like silicon carbide. So then you get a large bulk second-order nonlinear susceptibility, and you have to disentangle this from the E-fish signal here. This is also an interesting paper here on the right, lower right. It's not from us, but it has been demonstrated then that you can see even buried interfaces, buried oxide interface in this case. And here you have two examples, 10 angstrom RMS roughness and 3 angstrom RMS roughness, and you can see a dramatic difference in the signal. Of course, this atomic scale roughness is related to defects, and this is in the end what you sense with this. We also work more on the theoretical side. So this is more the high level TRL of our proposal package, let's say, where we have a path for some ideas for that we could implement into machines or into maybe process development machines. I don't really see this in the fab, but for process development, I think there are many interesting use cases here. More on the low TRL technology development, we're looking into how this can be used for structured wafers. So sub-wavelengths, nanostructures, what happens there? And we are looking there into the simulations first, and we look at something that is called ferroelectric domain walls, because this is our toy model to understand the nonlinear signal generation on structured samples. Ferroelectric domain wall is special because it only has a nonlinear interface, and there's no linear interface. This means the refractive index is the same, but the second order susceptibility is different because the crystal rotates 180 degrees. And then there's a phenomenon called Cherenkov phase matching, where basically the signal creeps along the interface and has phase matching condition, and therefore it gets very strong. And then in the end, you get 2 outgoing beams that you can detect. And we solve basically a theoretical problem about the polarization physics that happens at this interface. So this was disputed, and we can now fully simulate what happens in the experimental data. The experimental data for this toy model typically comes from lithium niobate and KTP, periodically poled, which has a different use case for quasi-phase matching, basically. But we use this in the configuration where we propagate along the interface, basically. So we learned a lot of things from these toy models and set up our basically numerical simulation code base, and then want to transfer this to real-world samples away from the toy model. This Cherenkov phase matching that I explained here can also directly be used if you want to image ferroelectric domain walls. So this has been demonstrated, but this is also not by us, in this very interesting paper here, where you can see 3D images of these domains, basically. In any case, what we then want to do is to apply the so-called Cherenkov phase matching condition to basically E-fish. So let's say you have a structured wafer, and then you have like side walls here. And on these side walls, it's also very critical to understand defects or the interface quality there. So when you have a space charge region due to trapping of charges at the side wall, we want to find the right polarization, wavelengths, and wave vector configuration to basically enable the same mechanism that happens at these ferroelectric domain walls. And therefore, we hope to be eventually able to make a phase matching along the side walls, and therefore generate very strong second harmonic signals depending on the defect situation and the local charges at the side walls, to then be able to, well, defect them at such complex nanostructures. So there could be a lot of applications in terms of when you think about FinFETs or nanosheet FETs, so basically on a transistor level. Yeah. And I think this is already it. So if you find any of this interesting, either the integration or towards this, I call it nonlinear scatterometry, maybe, If you find any of this interesting, then please get in touch to discuss about various funding things that we want to start soon. Thanks a lot.